Today, we're going to talk about an experiment that just completely blew up everything we thought we knew about the atom, and really about reality itself. We're talking about Rutherford's gold foil experiment.
Okay, so let's set the scene. Imagine it's the turn of the 20th century. Scientists know that everything is made of these tiny little things called atoms. But what are the atoms themselves made of? That was the ultimate question. It was like this giant locked box, and everyone was trying to find the key.
So what do they even think was going on inside an atom? The hunt was on to figure out what was hiding in there, to see the unseen.
Now, by this point, they'd figured out a few things. They knew about protons, which have a positive charge, then there are electrons with a negative charge, and finally, neutrons, which, you guessed it, are neutral. No charge at all. Now, I want you to hang on to that positive charge idea. It's going to be super important in just a minute. And this is where the physicist Ernest Rutherford comes in. He came up with this absolutely brilliant idea. This experiment that was kind of like being a detective, you know? The plan was to fire these tiny microscopic bullets to see what was really inside the atom. So, picture this. The setup was actually pretty straightforward. You've got a source on one end, basically shooting a beam of particles. In the middle, you have this ridiculously thin sheet of gold foil. I mean, we're talking just a few atoms thick. And then, wrapped around it all, was this detector screen that would light up with a little flash every time a particle hit it. So what exactly were these bullets they were firing? Well, they were called alpha particles. And all you really need to know is that they're basically the heart of a helium atom. 2 protons, 2 neutrons. But the key thing, the most important part for this whole story, is that they have a strong positive charge. Now, based on the big theory at the time, they called it the plum pudding model, scientists had a pretty clear expectation. They thought these positive alpha particles would just zip right through the gold foil. No problem at all. Why? Because they believed the atom's positive charge was all spread out and kind of mushy, like a pudding. There wasn't anything solid in there to stop it. But what happened next was, well, it was a total plot twist. One of the biggest in the history of physics, really. The results were not what anyone was expecting. At all. It was absolutely shocking. I mean, yeah, most of the particles did exactly what they expected. They went straight through. But then, every once in a while, bam, a particle would get deflected at a huge angle. And what was even crazier, a tiny fraction, something like 1 in 8,000, would hit the foil and bounce almost straight back. Rutherford himself said it was as incredible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. Just imagine. Okay, think about it. This could not happen if the atom was just a soft blob of positive charge. The only way a positive alpha particle could be knocked back so hard is if it ran into something else that was also incredibly dense and also positively charged. You know, like trying to push the same ends of 2 powerful magnets together. This rebound, this was the smoking gun. So this totally unexpected result led Rutherford to a conclusion that just changed everything. He'd cracked the case. All right, so here's what he figured out. It boils down to 4 huge takeaways. 1. Since most particles just flew right through, the atom has to be mostly empty space. 2. All that positive charge and pretty much all the mass must be crammed into one tiny, super dense spot right in the middle. He called it the nucleus. 3. The electrons, they must be out there somewhere flying around in all that empty space. And 4. Those crazy deflections, the ones that bounce back, those were the super rare times an alpha particle scored a near-direct hit on that tiny nucleus. But you know, the craziest part of all this wasn't just that there was a nucleus. It was the realization of how incredibly empty the atom is. And when I say empty, I mean the scale is just, it's hard to even wrap your head around. The nucleus, where all the stuff is about 10 to the minus 15 meters. But the whole atom is 10 to the minus 10 meters wide. That difference is just immense. Let's put that into perspective, okay? The atom is about 100,000 times wider than its nucleus. So, get this. If the nucleus was a tiny piece sitting in the middle of a giant sports stadium, the edge of the atom would be way up in the nosebleed seats. Everything in between, just empty space. And just like that, this one experiment completely destroyed the old plum pudding idea and gave us the atomic model we still use today. You know, the one with the little nucleus at the center. This was the foundation for, well, pretty much all of modern physics and chemistry. And that leaves us with this incredible question to think about. If the atoms that make up you, me, the chair you're sitting on, if all of that is 99.999% empty space, then why does anything feel solid? Why can't you just push your hand straight through your desk? But hey, that's a puzzle for another time. Thanks for joining me.